tutorial. And
they might have to turn it on.
Maybe
They do it from there. Oh, yeah, they both have to be on.
So in part 2 of the tutorial, I just had a chat in the break, and Aaron was telling me that they would do a noisy version of the selection instead of using a random split of the data for selection. And I'll start exactly what happened.
So whiteboard talk now.
I don't know why it...
It's still plugged in.
Yeah.
Good.
So I'll start this tutorial by showing you that doing the selection on a random split of the data and doing a noisy version of selection with a specific noise scheme are actually asymptotically equivalent. So what I hopefully convinced you in part 1 of the tutorial is that maybe carving is the right way to go, which achieves like best of the two worlds, both splitting and Lee et al. Okay, so let's look at this example of carving. So again, we are back in our toy example, the lasso, just that now I randomly choose a fraction of the samples to run my lasso on. Now I can write this lasso objective as an objective on the entire data. So I express the Gaussian law in terms of the entire data. I added, subtracted this term basically. And what is rho? Rho is basically the fraction of my data points that I'm using in selection. It's n1 over n. Say I'm using half of my data for selection, then rho is just half. So I can interpret this quantity. So I still have the same objective. I added, subtracted a term, which is the loss, Gaussian loss based on the entire data vector. So I can interpret this as a randomization term, basically. Actually, that's not completely correct. I can interpret the gradient of this thing with respect to beta as a randomization term. So there is a typo in there. And if we look at the gradient of this term and interpret it as some randomization, then it's easy for us to see that this is asymptotically Gaussian with mean 0 and some covariance matrix sigma. It's just basic asymptotics that you can try and see that the gradient of this term happens to be asymptotically a Gaussian random variable with mean 0 and variance covariance matrix sigma. So what carving is...
Stop. I want all of us to get onto this page.
Yes.
So, since this is somewhat foreign, where should I think of the randomness as coming from?
It's coming from the splits. From the fact that you have randomly chosen a split of the data on which you conducted your selection. So I'm casting it as this optimization problem. So say LASSO, for instance, but you could imagine any objective that you're trying to minimize. And I just say, okay, I ran this lasso on this random fraction of the data, but I do a little math, like I add, subtract a term, and if I...
So let me ask a couple questions.
Yeah.
So when I do the split, I have a choice. I can split into two equal size sets, or...
So that is determined by this...
How does that choice of whether it's tiny versus large, how does that affect the variance of the Gaussian?
It does affect. So this Gaussian distribution is a function of rho, which is basically the splitting fraction, the fraction of your data points that you use for selection. And there is a trade-off between selection and inference. So the more the data you, of course, use for selection, you are using up more information during selection, and you're left with...
Now, the next question is this noise Gaussian because of what we're computing, because we're looking at LASSO, and if we were doing some...
No, it is not. It is pretty general in nature. It just comes from analyzing the asymptotic distribution. You can see it like in the simple case, if I just tell you that, I mean, you can check this yourself. So let's look at this simple example where I was, say, I have observations which come IID from some distribution F. My selection criterion is root n y bar greater than lambda. This is basically our Z statistic in statistics that we call. So we are inferring about the mean of this distribution F, say, if the Z statistic happens to be greater than lambda. So instead of this, say I use instead a random proportion n1 of data to do my selection. So this is my selection criterion, right? Now what I would say, like if I rewrite this selection criterion as root n y n1 n bar plus subtract this term basically, then you can see that this term is asymptotically a Gaussian because you're just looking at square root n1 bar minus the difference of mean scale by square root n. And you get the right scale to randomize, you get the scale of this randomization error, which is asymptotically a Gaussian, by just analyzing the distribution of the difference of the means. So that's where it intuitively comes from.
So maybe you're going to go in this direction, but like the way you wound up the previous tutorial, you said, okay, rather than trying to select based on the whole data and conditioning on the whole data, we're going to select based on part of the data and look at the conditional distribution of the entire data set and condition on that event.
Yes.
In some sense, what that is doing is saying, okay, at some abstract level, you're just taking a different selection procedure, right? Rather than using the whole data and running LASSO, you're running LASSO on a random subsample.
Yes.
The sort of possible design space of selection procedures is much larger than that, right? There are like, lots of different things you could do. Presumably, when you're choosing this design procedure, you're optimizing for something, and I guess my question is, and maybe you'll get there, is like, if I don't, suppose I'm not married to LASSO, I don't really care about LASSO, I just want to pick the best design procedure, the best selection procedure, what should I be?
I am not, so I am not very concerned about, like, I'm not the one who is doing the selection, but I think, like, to answer your question, I'm exactly not the one who is optimizing over the selection objective, but I think it's somewhat related to Cynthia's question of like determining this row, because there is certainly a selection trade-off between selection and inference, which is determined by this row parameter. So there is a question of how do you want to fix the scale of randomization, which depends on basically this row parameter. How big of a subsample that you want to take. So there is this trade-off, and when I analyze the data set, I can tell you like the rule of thumb that I use is that I check the non-randomized selection and I try to be not too different in my, like my findings don't turn out to be so different from the non-randomized selection. That's what I care about, because I don't want to randomize my objective to a great extent that I lose all the signals and I report completely different findings from what I would have gotten without the noise. So I don't want to add so much noise that I get a completely noisy selection.
Condition on this way of choosing row?
No. So no. It's not data snooping. Like I do use, but I don't. All I want to say is that I'm not like using a very principle, I'm not optimizing some objective to determine row here, which gets me some optimal trade-off between selection and inference. So there is certainly room for getting some principal way of choosing this row. I'm just telling you a rule of thumb that typically gives me selections that are not very different from the non-randomized analog. but I'm not like actually working out an objective function which I'm optimizing to get like an optimal row that gives me some sort of a selection inference trade-off yet.
And just a quick question to make sure I understand. So this connection between like random splitting and Gaussian noise addition.
Yeah.
The variance of the noise is like a data-dependent quantity, right? Because if the, like for example, if the data was entirely homogeneous, then
no, this is not a data dependent. It just depends on the factor rho, which you determine like.
But like suppose all of the elements in my data set were the same, then there would the random split would have no randomization effect because no matter what half I took, I would have exactly the same data set, right?
So every x is the same and every y is the same.
What you said.
But you're.
It's the same thing.
It's definitely data.
But
Or at least
I guess
underlying
you'd.
distribution.
It depends on the underlying distribution of the data, of course. It depends on f, but yeah, it's this asymptotic variance is determined by rho, like that's the parameter that it has. But let me get to that question, I think a slide later, it becomes clearer. So all I wanted to tell you is that Gaussian randomization scheme is something very natural that comes up from this carving idea. But let's see a more mathematical formulation of it, which makes it maybe a little more clearer. So just want to mention that Yan and Taylor, which actually introduced randomization schemes in selective inferential literature, dealt with randomizations that have much heavier tails, like Laplace and logistic, and they did not talk about Gaussian randomization in particular. But I personally run all my examples with Gaussian randomization, and I find it more appealing in nature because it's something that comes up very naturally from this data carving idea. So let's look at this randomization scheme. I think this objective will make it clearer. So if you run LASSO with a noise objective, with a noise term which is linear in parameter beta, where omega is drawn as Gaussian noise centered at 0 with some scale tau square. So the scale tau square is essentially related to the splitting fraction rho. I can give you the exact expression how rho is related to tau square because that's what we saw, that data carving was asymptotically equivalent to this objective where omega was Gaussian with some sigma parameter. So maybe this is more palatable to people here. You see it as it's termed as objective perturbation in differential privacy literature. And it's just form of randomizing your optimization objective. So I'm going to even if it's not a LASSO, it's some loss and some penalty, I can just add a linear term in my parameter with Gaussian noise.
I guess getting back to my last question, for differential privacy, you would pick the variance of the Gaussian noise to be something that was independent of the data distribution, whereas in the
Tau square is not dependent on the data distribution. I could fix the scale of tau square however I want, depending on the extent that I want to randomize my objective.
If your data distribution was degenerate, you would get no randomness at all by randomly splitting the data.
But am I interested in
But that's just an example that shows that the variance has to depend in some way on the data distribution in this equivalence.
I don't see how tau square is dependent on it's a scale that I fix. It's a scale that I choose. So and that's just determining the extent to which I'm willing to randomize my objective, to make it noisy to what extent. So it's not really something which is...
So you choose it when you're explicitly adding noise.
Yes.
But when you're... This equivalence from the last slide, which maybe I don't totally understand, where
it's dependent on rho. Rho is the splitting fraction. That's again something which I determine explicitly. That's not dependent on the data generative distribution. I decide whether I use 50% of the data samples for selection or 80% of the data samples for selection.
Not to belabor the point, but again, if my distribution, for example, had just put probability 1 on the same XY pair, so my data set was just n copies of the same XY pair, it doesn't matter what half of them I take, I'm going to get the same data set. So there's no randomization at all, right? I just have a deterministic procedure now when I take half of them and run LASSO.
Right. No,
fraction
Aaron,
is independent
what
of
you're
the
saying
data
is correct, that if you try to think of data splitting as adding noise, then it is
It might not give you like,
depends on the data set,
Right.
and that is fine. And now we're looking at a procedure that doesn't,
Okay.
where tau is specified in a way that.
Okay, great.
yeah, it's just a scale that I determine, and if your data points all happen to be same, and this, I mean, I feel all the inferential principles should still go through as long as I'm determining tau, or rho in the previous example, but it might be that you might get meaningless selection and meaningless inference depending on how good your data sample happens to be.
So I'm totally on board when you're explicitly adding. So maybe that's fine for going on.
So the question is, if we have if this is the sort of randomization schemes that we look at, whereby we can get a more generalized version of data splitting in the sense that now we condition on this randomized selection event, on this noisy version of selection event, and try to provide inference based on it. The question is now more computational. Well, we saw the Lee et al., which gave us a univariate truncated Gaussian pivot, and it was explicit. And there was no asymptotics involved in there. It was just a finite sample guarantee if you had really Gaussian data. Now the question is, could we have something like the polyhedral lemma coming to our rescue even here? So let's look at the randomized lasso objective. So it's very similar to the canonical lasso objective, except that now it has this linear term in the parameter. So the selection by lasso is equivalent to, again, a set of polyhedral constraints, except that now selection is described in terms of both your response and randomization noise omega. Yes?
So there's one thing that's going on. Is all of this sort of conditioning on the matrix A as known and fixed?
So A and B would be functions of what you select. So they would be functions of E. Say E is the set of active coefficients you report. They are certainly functions of selection. They're determined, so whatever you select is equivalent to the fact that I select, say, 5 coefficients from lasso. That is equivalent to a polyhedral region A, which is a function of those 5 coefficients.
Let me try this again. I said the wrong thing. Are we thinking of X as fixed when we're doing the conditioning?
So in this example, yes.
Great, thanks.
Yes. But I mean, to answer your question, you can also do it with X random. So X doesn't necessarily have to be fixed, but in this example, I'm just taking a fixed design. So now if we look at the same conditional law, right? We are looking at the conditional law of our naive statistic, which was some eta prime y. This was the OLS, like a particular direction, say the first coordinate of the OLS estimator that we obtained by refitting a linear model to our data y and selected subspace x. And then we condition on the selection event, which is now a polyhedral region defined in terms of your response y and randomization omega. That's the only difference, that you have a randomization in the selection as well. And you condition again on the same nuisance statistics that don't give you any information about the parameter of interest. The point is that this law no longer happens to be a truncated Gaussian anymore. And to see why it's not so, so if we had a fixed, just imagine that if we have this polyhedral selection region at a fixed realization of omega, say omega 1, then of course, you know, you again, like by conditioning on your nuisance statistics, you can see that eta prime y would be restricted between gamma minus and gamma plus. But as you can see that the selection is actually marginalizing over these omegas. It's not a fixed realization of omega, but the selection probability that we are computing here is randomizing both over the data as well as the omegas. So if I were to compute it at a different realization of omega, which is omega 2, I'll get another ray to which, a different ray from this one, to which eta prime y will be restricted to. So it's not a single polyhedral region, like it's not a single ray that my naive statistic is no longer is restricted to. So as a result of which, I cannot express my selection event in this form, that eta prime y is restricted to a fixed polyhedral region, to a fixed ray, gamma minus and gamma plus. But these gamma minus and gamma plus are now random quantities which vary as you vary your realizations of omega, which is a random quantity. So the polyhedral lemma of Lie basically breaks down here. So what's natural here, you might say, is that, okay, we might run a sampler from the law of eta prime y and omega truncated to the selection region. So I have a selection region which is basically a polyhedral region. So I can instead run a sampler because I don't have an exact pivotal quantity anymore since the polyhedral lemma doesn't apply. Does this look very mysterious? It's just that now I have this, the rays that I was truncating to earlier, I cannot get a single ray to which eta prime y is truncated to. Rather, there are multiple rays which vary as I vary the instances of randomization. So instead, what I can do a natural way is sampling. I would sample the law of eta prime y and omega jointly, restricted to the selection region that I described to you. But this is something that we have in this paper, but I kind of am more, I like MCMC free inference. I'm not so comfortable with samplers because I never know when it's really, when my sampler has converged and when is it giving me credible inference. So to provide MCMC free inference, let's look at this randomized law. Let's try and compute, let's understand what this randomized law is, and let's see whether we can avoid a sampler in some ways.
So this means coming up with like a provably computationally tractable way to sample from the right distribution?
No sampling involved. So I'll be talking about, so this paper actually talks about a sampler which is essentially trying to truncate from this randomized law, truncated to the selection region or the polyhedral region. But I'm going to talk about MCMC free inference and
no, like sampling free inference.
Yes, sampling free inference.
Like the previous slide, you said, okay, it is not, like the selection region is not an interval. There's no,
there is no
wrong way to think about it. Now, it just, so, and the, okay, I understood that slide. Now, but now you're saying what Tian et al. Did was to select from, like, I didn't understand what you said they did.
Go back a slide?
I think forward.
Or forward? Sorry. Yeah.
Keep going.
So there is no closed form expression for a pivot anymore. So we don't have a pivotal quantity.
Can I finish the question?
Yes.
Can you go forward one more slide? Like, what is, I'm trying to understand the text in blue.
Okay, what is sampling from the...
What do you mean by that sentence? No.
Yes, no, to explain that, I'm going back here.
Okay, is it the case that you're saying sample a random omega and then pretend that's the real omega that was used? Or
No. So you have a, so you can precisely sample from, so you have a joint law of data and randomization. So let me try and let's go back to the simplest example where I have, say I was talking about root n bar greater than lambda. So now instead of this selection, I'm looking at this greater than lambda, right? So what is my selection, what is the selection adjusted law that I'm looking at? Actually, I would have written the law just few slides later. Maybe that would be better. I can just go and explain to you what is the law that I'm sampling from. After I explain, I'll go there.
Just to understand, so maybe I don't need to understand exactly what they did, but
I'll give you
from the correct distribution.
From the exact distribution, but of course you would
We're just
sampling. So you would have error coming from your sampler because you're sampling, but you're sampling from the exact law. So I'll get to that in few slides. I think you'll understand that better once I show you what that law is.
And the point is, you don't want a sample. You want like an analytic computation of the thing you're after.
Yes, I'm avoiding a sampler, but like you will see that we will need some need of approximation. And why does the need of approximation come into play? I'm going to explain that in a bit.
Thanks.
Okay, so let me not waste time here. So we have this randomized lasso objective. Now, coming to inference, I always have to talk about a model and the target that I'm inferring about. It's the same target that I've been talking about so far, but let me just go over it quickly. Just for consistency's sake, I'm not very happy with the saturated model, but for consistency's sake, I'm sticking to the saturated model that Lee et al. Used. This is also used in the Posey paper, where you assume that your data is generated as Gaussian with a mean mu, plus some Gaussian noise. This is the model that you're using for inference. Your selection output can be described as a function of your response y, data y, x, and randomization omega. The target that I'm looking at is the same old target, which is your population least square coefficient, the projection of the true mean mu onto the selected subspace of X. And again, because Lee et al. Does coordinate-wise inference, we just say focus on the first coordinate of this e-dimensional vector. So my target statistic, so I start with a naive statistic which we all use for inference, which is the first coordinate of the least square estimator projected onto the selected subspace of X. Naively, if there was no selection, this would have been Gaussian. But the question now is, what is the right law of this naive statistic if we did perform selection? How do we calibrate the law of this statistic? Okay, so to see it, let's simplify notations again. So we have, say, data, a statistic z, which is a function of data. We have randomization omega. Now, what is the unadjusted or the pre-selective joint law of data and randomization? So in this case, I just use some Gaussian noise. So this is my Gaussian law for randomization. And it was independent of the data. So, and this is the Gaussian, say, z is just univariate Gaussian with mean parameter b that I'm trying to infer about and variance sigma square. So this is the pre-selective law, Gaussian law of data and randomization that I start out with. Now I know that selection constrains my data and randomization to lie in some selection region K. In the case of LASSO, it happens to be a polyhedral region, right? That's described both in terms of my data as well as randomization. The question is, what is now the adjusted or the selection adjusted joint law of data and randomization? So we started out with this pre-selective law. The selection adjusted law is just the same law, is proportional to the same law truncated to a selection event. And the selection event depends on you, is determined by the selection that you carried out on the randomized version of your data. So this is the adjusted law that I'm looking at. This is what it's proportional to. So if I run a sampler, I'm going to sample Z and W from this truncated law. This K, the selection region, is determined by the selection based on that particular realization of omega that I carried out, but that gives me the selection adjusted law, and I now sample instances of Z and W from the selection adjusted law. That's what a sampler would do, if that makes it clear. Okay, so now let's look at this density a little further. So what I'm interested in is inferring about parameter B. So what is the marginal law of data conditional on this selection event? So the marginal law can be obtained by just marginalizing over the randomization part, right? This is the joint law. I integrate out the W's to get the marginal selection adjusted law of data condition on selection. So once I integrate over W, what I get is this factor that probability randomization lands in the selection region, conditional on the data value being Z, right? This is just obtained by integrating over omegas. So if I look at this selection adjusted marginal law of the data, I see that this is an exponential family of laws. How does it compare to the pre-selective Gaussian family of laws? So it is, again, it has the same sufficient statistic as the Gaussian law. It has the same natural parameter as the pre-selective Gaussian law. But what is different here is that the Gaussian, you have a different reference measure. You have a reference measure that is equal to the Gaussian reference measure times another function of your data. And that other function of your data is precisely this probability that randomization lands in the selection region conditional on data. So you have this conditional probability of randomization landing in a selection region. So if I want to avoid a sampler, why can't I try and get a hand on this quantity? Unfortunately, even for LASSO, this probability doesn't have a closed form expression. It's like I have like the multivariate Gaussian volume of some region, and I don't know a closed form expression for it. So I resort to approximation. So if I get a reasonable approximation that has some guarantees and gives me a reasonably good form of this probability, why can't I just use it and avoid using a sampler? So that's what I'm going to describe next. So I hope this slide just gives us a sense of what the randomized law is. So if I were to do a sampler, I would go back here and just sample from this joint density and discard the samples of randomization because I don't use them for inference. But instead now I'm saying, okay, let's just compute the randomized law and let's see what is really the intractable part in this randomized law. Can we go around by giving some tractable quantity for this intractable component with some reasonable guarantee? So I use an approximation to compute this probability, to be precise. Now, what is the guarantee on this approximation? So if we have a convex and a compact selection region, then the guarantee on this approximation is that the difference between the log of this approximate probability and the log of the true probability goes to 0 when scaled over 1 over n. So people who are already aware of large deviations, what this tells you is that the approximate probability that I compute captures the true rate of exponential decay of the exact probability.
Sorry, what's p hat?
P hat is the approximation that I use. I haven't told you what approximation I use, but I just tell you what's the guarantee on the approximation.
At the beginning of the theorem, there's a statement like, for the p hat in our paper, this statement.
Yes.
Got it. All right.
Yes. So it just tells you how close, like, are you really capturing the exponential rate of decay of the true probability or not? And that's what this tells you, that it does it on a large deviation scale.
And is there any...
It's a point-wise convergence.
There's no, like, p or anything in this statement. Is that, like, it's independent of the dimensionality of the problem or the number of significant features or anything like that?
The asymptotics is in the sense of fixed p and n going to infinity.
Okay.
Yes, that's the sense of asymptotics. Now let me give you a sense of how we compute this approximation. So to compute this approximation, all you need to know is the KKT map of the objective that you were solving as your selection query. So this KKT map is a function of randomization, your data realization Z. And you can see some variables O, so it's an affine map in Z and O. So what are O? O are optimization variables. To be precise, in the case of LASSO, optimization variables are your subgradient variables. They are your active signs and inactive subgradients which are constrained to lie in a cube. So I can compute the KKT map, and the second component that I need to know to compute this approximation is the conjugate of the log MGF of the randomization that I use. So in this case, I use a Gaussian randomization. So the conjugate of the log MGF of Gaussian randomization is pretty simple. It's just this quantity. So my approximation is precisely given by this quantity, which is a convex objective. So the first part you can see comes by evaluating this conjugate of the log MGF of Gaussian randomization at the KKT map. And then I have another function which I can compute explicitly. I won't tell you what that is to complicate matters. So my take-away message is that the approximation that we compute here is pretty easy to compute. It's just a convex objective. It's constrained to lie in a region that is also fairly simple. So in the case of LASSO, it's just like sign constraints. So it's typically constrained to lie in some orthant. That's not very hard to compute as well. So, and I don't use this constrained optimization. Rather, I replace this constraint with a barrier function in my objective so that it smoothens the objective, and that's much easier for me to handle. I just use a gradient descent to solve this approximation each time. So to give you a little bit of intuition about this approximation, so what I was trying to, so the reference measure, the intractable component in the reference measure that I was approximating was this probability that randomization landed in a convex selection region. That was what I was trying to approximate. And here randomization has mean 0. So what this approximation basically tells you that this probability can be, log of this probability can be approximated as the distance of origin, which is the mean of randomization, from its projection onto this convex selection region. So this is the basic intuition of the approximation. Now to just show you the simple example where we have univariate Gaussian, which is say mean B, and we have this thresholding event where I look at a randomized version of the thresholding event. So in this case, I can compute the exact reference measure, right? It's just a Gaussian tail. In the simple problem, I know what the exact selection probability is. So this is the exact randomization density, which I can afford to compute in the simple example, but not for general selection rules like LASSO. And this is my approximation that I actually use, just to give you a demonstration of how good the approximation behaves in comparison to the exact law. So this plot plots the approximate laws, which are in green, and the true density, which are the dotted blue lines. And these are for different parameter values. And you see that the approximation actually does a very good job in mimicking the true or the exact reference measure. So to obtain, I'm not going through it again, but you can just construct a pivotal quantity. So once you have this intractable, you have plugged in an approximation for the intractable probability that you did not know, you have a hold on the randomized law. And you can construct a pivotal quantity from it by simply looking at this observation. And to compute intervals, you look at all parameter values which satisfy this. So confidence intervals construction is pretty trivial from here, but now I want to move on and talk a bit about point estimation. So how do we obtain a point estimate that overcomes selection bias? So if I again go back to the randomized law, what I had in that law is, so if I knew that the randomized law belonged to an exponential family of distributions. If I look at the log partition of that exponential family of distribution, then it would be given by this quantity. And again, the only intractable component was this probability of randomization landing in the selection region conditional on data. As a result of which I couldn't compute the selective MLE. But now with the approximation, I can just plug this approximation in and solve for the approximate selective MLE. So what I obtain with my approximation is an approximate family of exponential laws, which is hopefully close enough to the exact family of randomized laws. So a good feature of this approximation is that it yields a convex approximate selective. The selective MLE objective that you solve happens to be convex in nature. But what are the guarantees associated with this point estimate? Well, for a convex selection region, we see that the selective MLE actually happens to be a globally consistent estimator. And in particular, it happens to be consistent for non-local sequences of parameter. Now, I don't want to go into the mathematical details of it, but just want to point out that non-local sequences of parameter is basically a regime of inference where it's very hard to obtain consistent estimators. So for instance, the knife point estimate is certainly inconsistent. If you look at the OLS estimator, that just happens to be inconsistent, very trivially. But if you did not use randomization and you use the selective, so the Lee et al. Is also a conditional law. So if you try to maximize that law and obtain the MLE, then the MLE there would be inconsistent in these regime of inference. Yes?
I don't know if it's important. I don't know what non-local sequences of parameters are, but like if it's
no, I can just
crucial for the later discussion? Or?
No, it's not. It's just a regime of inference. So you look at CLT for local sequences of parameter, right? CLT, you look at an order 1 over root n neighborhood of mu. You look at local neighborhoods. But non-local neighborhoods are things like, say, so if root n mu n were bounded, so this would be, this is when I'm looking at a 1 by root n neighborhood of the actual parameter. So this is called local sequences of parameter, but non-local is, say, I fix mu n to be mu, say mu is -1. Then root n mu n basically goes to minus infinity as n tends to infinity. So this is a non-local sequence of parameter. If I fix mu n to be mu, which is just -1, that's a non-local sequence of parameter where root n mu is converging to minus infinity as n tends to infinity. So that's a regime of inference where your selection events are becoming rarer and rarer and rarer, and it's becoming harder to provide inference. So even in those hard regimes, I'm claiming that the selective MLE based on this randomized law happens to be a consistent estimator.
You're saying in general, look, if I just try and understand what the second X is telling you, what you're asserting with the second line where you're saying
So I'm saying if I just use the Lee et al. Conditional law, which didn't have any form of randomization in it, you were conditioning on the selection event based on the data. And if you compute it, you could also maximize that law and try and compute the selective MLE from that law. All I'm saying is that that selective MLE doesn't have desirable consistency properties. It's not a consistent estimator.
So again,
in the rate of consistency, how does the randomization property tau come in?
In the rate of, okay, so why, to give you an intuitive sense why the randomized law just yields a globally consistent selective MLE whereas the non-randomized law doesn't, an easy way to see it, the non-randomized law is not a smooth law. As you can see, it's just truncated, like you have this Gaussian law truncated to the selection event. It is putting mass 0 outside the selection region. And that truncation is just like a 0-1 truncation, like you have mass 0 outside the selection boundary. It's not a smooth law. Whereas this randomized law happens to be a smooth law. So
any tau larger than 0 will give you a smooth law?
Yes.
But this, having larger tau make it make the rate of consistency.
Because tau, you are not varying it. It's if you fix tau, then the rate of, it's not varying with n. So I don't see the rate of consistency changing. But if I make it a parameter of n, then if it is also varying with the sample size, then I should expect it should affect the rate of, like the rate of consistency should depend on tau if it's a function of the sample size.
So just to, again, to sort of try and, before we get too far away, just to understand that second assertion, the little red X, that you say there's some natural set which if you condition on you run LASSO, you take the non-zero
selection,
non-zero coordinates or the coordinates that are big enough or whatever it is you do, and now
All I'm saying is that if that selection was,
conditional on that event having occurred,
yes,
you will not
get a consistent MLE. If you were to compute the MLE of that law, so that's also a law. It is again another exponential family of laws. But the thing is that the reference measure there is not smooth. So it's not a smooth family of laws. That's the reason why the MLE happens to be very unstable in those cases. And it doesn't have desirable consistency properties. You can basically construct a counterexample to show that it is inconsistent. And the thing that is making the randomized law win over the non-randomized law here is just the smoothness part. The smoothness is contributing to a consistent selective MLE.
Yeah, I guess one of the things that I'm confused by is like, if tau goes to 0, then you'll eventually
yes.
estimator, and so somehow there's like
if tau is converging to 0, that's a pathological case, yes. But we don't even, I'm not very sure if intuitively it makes sense if tau goes to 0, probably you expect these randomized laws to converge to the non-randomized law, but I think the mathematical proof of this still needs some part where you have weird conditions coming up and they're not very easy to verify. So I'm not very confident about making statements in those regimes, yeah. So it's basically consistent at a rate which is slightly less than half. So any rate that you take which is slightly less than half, it's consistent. But this consistency of the selective MLE, I realized just a month ago, has some very nice property associated with Bayesian post-selective inference. It actually is very closely related to posterior consistency. It's something that I should have realized much earlier, but I really like the selective MLE also because if you were to now do inference in a Bayesian model instead of a frequentist model, it gives you desirable frequentist guarantees in the sense that the Bayesian randomized post-selective law that you construct happens to be consistent because the selective MLE starts concentrating around the right parameter. So maybe I'll skip over this section where I thought I would describe the selection that goes on in the EQTL example where I basically applied this approximation. I can just give you the gist. So like I already told you, in the first stage, you marginally screen the eGenes where you compute marginal correlations of each gene with the set of local variants around it. You compute p-values based on these marginal associations, and you are testing a global null that this gene has no association with any of the variants around it. So you can you can construct a Bonferroni or Symes global p-value. And once you have a p-value for each of the genes, what you do is pass the p-values through a BHC. And that's how they try to control FDR at the level of eGenes. So this is basically describing the selection. And once you have the eGenes, you run a LASSO for each of the eGenes to report e-variants. I'm skipping over them a bit. And this is basically to give you a snapshot of how the inference compares. So we saw that naive inference was bad. This is just Lee which is adjusting for LASSO, which is just one stage of the mining because you have mined the eGenes and that's not LASSO. So that's why you see that Lee LASSO really falls short of coverage because it's not accounting for all of the selection here. Whereas this approximation method that I implemented is adjusting for this hierarchical mining, both the screening of eGenes and e-variants, so it's giving valid coverage guarantees.
Can you go back?
Yes.
Sorry. So you're saying it gives valid coverage guarantees, but
yes.
If I look at the 0 column?
Yes, there is a bit of computational instability here that the coverage is around 83%. So the target is 90%, whereas all these are like more or less good. It's slightly less here, it's around 83% because of some computational instability. I forget what it is exactly, but
sampling-based approaches that you described, like Tian et al.
So we never tried the sampling approach here because still this was a very high dimensional problem and the sampler isn't that developed to deal with really high dimensional problems. So we didn't try it here. I rather tried my approximation method here, so I don't know. The sampler is currently still not in a stage where you can apply it for really high dimensional problems.
So here you have the condition on the event of being included in the BH selection.
Yes. So there are actually...
So that's different from what you showed before. That's a harder...
That's a harder selection, but I can still describe that selection, yes.
Similar kind of approximation will work?
It's an optimization objective again. I did not talk about what optimization objective, but okay, so let me go over that slide and just come over to the point that whatever I'm doing here is actually very general in the sense that it's not committed to just the lasso. You can like replace it with any loss you have and any sort of penalty, any sort of convex penalty typically, because that gives you convex selection regions and you can interpret those selection regions geometrically much better. So the BH selection can be cast as an optimization objective again. Like the whole marginal screening together with the BH, it can be cast as an optimization objective with a convex loss and a convex penalty.
I see. And how much noise did you add here for this experiment?
So the ratio of my noise scale to the estimated noise in the data was 1/2. And I just went with it, like I don't have a principled way of choosing it. I just fixed it at 1/2 and I computed the non-randomized analog, like I did all the process without adding any noise, and I saw that the selections were very comparable. So I did not look for any other tau, I just went with that choice. So it's still a very ad hoc way of choosing tau. We should have more principled ways of choosing tau, maybe something like he suggested that we should look at maybe some optimization objective that tells us the trade-off between selection and inference.
How much did you lose in power for this value of tau?
So there are powers associated at both stages. So what do you mean? Like we do gain in inferential power, but we lose selection power, right? Because we are doing slightly noisy version of selection. So surprisingly, like I said, I just fixed it to be 1/2 and I checked the selections, I compared the selections with the non-randomized analogs without using any selection, and both at the stage of screening eGenes and eVariants, we were doing better than, we weren't doing very different from them. To be precise, at the stage of eGenes, we select even more eGenes than they do. And that's because this BH happens to be more, like it just tends to be less conservative when you add a little bit of noise. And it was actually suiting us more even in the eGene stage. It was making BH be a little less conservative, but at the evariant stage, we were over-selecting a bit more. We were over-selecting a few more noise variables, but we were actually capturing as much signal as they were. As far as simulations go, I don't know what it is in reality, but that was the outcome of simulations. So as expected, again, the length of intervals of the approximate method happens to be pretty much better than the Lee et al. Intervals, 1.5 times shorter than they are. And as expected, both these intervals are longer than the unadjusted or naive intervals because you pay a price for selection. And this is a comparison of the risks of the selective MLE with the naive estimates. And here again, the point estimator is performing reasonably well in terms of risk as well. So I don't know if I have time for this. Should I go on for a few more minutes or?
How many minutes do you feel would be good?
I'm good with 10 minutes maybe. I can try and wrap up in 10 more minutes, if that's good. So I told you a bit. So I told you so far about frequentist selection or selection in a frequentist model. Post all the selection, we described a Gaussian model on the data. But what if you were a Bayesian and you maybe had a prior on the parameters of interest that I discovered from selection? How can I incorporate inference in a Bayesian framework and give you Bayesian credible intervals and maybe a Bayesian estimator? So this is, again, I just want to go through this concrete example without going philosophically into why we might have a Bayesian model. It's as simple as that. Say you have a prior and you tell me, like, I have prior information on the parameters you discovered. How can I incorporate that prior information in my model? So let's look at a concrete example. So n is 200, p is 1000. I have a Bayesian data generative process. So I generate my parameters beta from this mixture model where it's a mixture of two Laplace distributions with probability 90. I draw each coordinate of beta from this Laplace distribution, which is very concentrated around 0. And with probability 10%, I draw it from another Laplace distribution, which is not so concentrated around 0. So I'm actually drawing a sparse vector beta, which is determined by this true prior. Now, once I draw my beta, conditional on beta and x's, I draw my y's again. And here, plus some, I'm adding some Gaussian noise to the y, so it's x beta plus some Gaussian noise. So what is my baseline method? My baseline method, I run LASSO, I discover E, and I forget about selection. I just go about doing the usual Bayesian posterior. I append a prior on my beta E, that is the parameterization that I discovered from LASSO, to this usual Gaussian model, which I assume like, okay, so selection did suggest to me that E is a sufficiently interesting selection event. Let me parameterize my model on Y by XE beta E. So this is my canonical method or my usual Bayesian posterior that I would work with. Yes?
Sorry. I'm confused here. So when you say unadjusted,
it's just, there is no, I'm just looking at the untruncated likelihood. So far I've been looking at the truncated likelihood, which was like looking at this likelihood truncated to selection. Here I'm forgetting about selection. I pretend that there was no selection. Selection did suggest to me a model and an interesting parameterization, but I forgot about, I'm not accounting for it in any which ways.
It's not actually a posterior distribution.
It is what people would do right now. So I just told you, okay, this is a set of interesting parameters. Maybe I didn't describe you the experiment, or maybe I did. And if you did not know anything about selection-adjusted inference, what would you do? You would append a prior to the likelihood on the data. That's what you would do, unless you have another suggestion for a more reasonable Bayesian posterior.
I mean, like by definition, the posterior distribution you sort of condition on the outcome of some,
no, you
condition
no.
on something.
You condition on the data, right? You condition on all of the data.
Okay, so I'm not trying to be difficult. I just I don't actually understand what you're saying.
Maybe you're confusing it with Bayesian variable selection.
I think the question is just, maybe we understand, yeah, this is sort of what people would do, and maybe it's hard to think about what else they should do, but what Adam's asking is, this is a heuristic thing to do that is not actually the posterior that an actual ideal Bayesian would come up with. This is sort of the best you can do with previous techniques.
Yes, that's what I mean, if I just told you, well, I had some pilot study and I ran this experiment, I ran LASSO, and there my goal was to discover some interesting structure in this data, and I basically discovered that probably these are the interesting findings. Now I come to you as a statistician, describe to you my experiment, and you tell me, well, okay, given these interesting parameters, I have a prior distribution, and maybe the likelihood I parameterized by this Gaussian likelihood with mean XE beta E. Let me try and do Bayesian inference on it. So,
the unadjusted posterior is what would happen if you sort of incorrectly did Bayesian inference, basically, by failing to take into account.
I guess it's yes. That's what I'm.
If you integrate over E, do you get back like the original prior?
If I integrate.
Somehow there's like a tight mismatch in my head between like what you're saying and what I think of as like Bayesian inference.
Maybe you tell me what would be the posterior maybe that
Like
you would
there's
use.
You started with a prior on beta. It's
Yes.
specified.
But I don't know, this is the true data generative mechanism, right? I cannot assume that I know the true prior. So I'm just saying like, I just described you a data generative mechanism by which I am generating my data points. But you wouldn't know it, of course. It should be a black box for you who is providing the inference. I'm saying that I use my data to discover some interesting parameterization, and at the moment I'm interested in giving some Bayesian inference about those parameters of interest.
I'm guessing there's just a language mismatch. Like by unadjusted posterior, you mean sort of unprincipled heuristic.
Yes.
And now you're going to tell us the right thing to do.
Yes.
Okay, great.
And but still, I think statisticians even now they would probably think maybe, I mean, even if you do like something like, I don't know, if this is your starting point of inference, we'll see where it can go wrong in terms of what sort of inferential metrics, but it's not apparently very clear, I guess, to people like how can it go wrong and where can it go wrong.
I think you're setting up a straw man, which you will like knock
Yes,
down.
yes.
And for us, like the straw man itself doesn't really make sense, but maybe that doesn't matter. Or for me, the straw man itself doesn't make sense to begin with, but maybe that does matter because you're going to show us something that like makes sense. Great.
So instead, like again, I mean, I run the randomized version of LASSO. So what am I swapping here? What am I comparing to? I run a noisy version of LASSO, and it suggested to me some interesting parameterization beta E. And now I look at the posterior that I'm looking at is this prior appended to the truncated likelihood that I was looking at. So the truncated likelihood was precisely the likelihood of the data. Then there was this reference measure, which was randomization satisfying the selection criterion conditional on data. But this is not a function of the parameters in your model, so this kind of gets killed. So what you have here instead is the selection probability, which marginalizes both over data and randomization, and it's a function of the parameters in your model. So this is a truncated likelihood appended to the prior. Well, is this the right thing to do? And that's what I'll show you. Maybe let's skip over the...
So like the difference here is you're conditioning on E.
The difference is that my likelihood is different from the previous likelihood that I used. So I was appending a prior. So in a Bayesian, as a Bayesian person, you have a model, you have a prior model, and you have a likelihood. So the likelihood there was the untruncated likelihood. I did not account for selection, and the likelihood in this case is this truncated likelihood. That's the effective difference between the two regimes.
So if you had instead of p hat, you had the actual probability.
I just don't know it in exact closed form. That's the whole point. If you did, yes.
Yeah. Let me try to finish the sentence. So if you had like the exact probability in the denominator there, that would be like Bayes' rule. It would be just like the natural.
It would satisfy all the Bayes rules, yes.
But you don't want to do that because computationally it's a problem.
And you don't know
We
it.
don't know that.
And you don't know it. You don't know what the
I mean, ideally, I would like to do that. If I had the exact probability, I would just look at the truncated likelihood appended to the prior. But the point is that, again, this probability, for the very same reasons, doesn't have a closed form expression. So my best bet is here, let me approximate this probability as a function of the parameters in the model. Let me nail down this probability as a function of the parameters in the model. And it's the very same approximation that I was using in the frequentist sense also, except that now this probability region is slightly different because it's marginalizing over the data as well.
I guess I'm trying to understand the distinction between things you're doing for computational reasons, which are fine reasons to do things.
Yeah.
But like it's
So I don't have, so this is the truncated likelihood, right? Without the hat, without the approximation.
Right. So if you didn't have the hat, this would just be like
The actual.
The exact,
actual conditional distribution.
yes.
And now what you're saying is the denominator is hard to compute.
So I plug in an approximation.
Good, thank you. But then you said like, and we don't know it or something like that. But that I'm trying to get at the distinction between like hard to compute and like fundamentally unknowable because there's stuff missing.
Yeah, it's hard to compute. The exact probability is hard to compute.
So I think we're going to
wrap up. Yes, yes, no problem. So I'm trying to wrap up. So basically here the computational cost in Bayesian inference would be essentially involved in computing this probability again. And it's similar in spirit to the approximation that I talked about in a frequentist sense. Just the difference was in frequentist inference, I was approximating the reference measure, but here this reference measure doesn't contribute to the posterior because it's not a function of the parameters in the model. Rather, what contributes to the posterior is this normalizer to the truncated likelihood. So if you believe me there, I'm not going into the, I want to show this one slide and maybe a slide after this. So let's compute, instead of FCR, let's now compute Bayesian FCR. So I really know in simulations what my true data generative mechanism is. So I generate my data this way. And I compute, once I construct the selected intervals based on this Bayesian posterior, selection adjusted posterior that appended the truncated likelihood to the prior, I compute the proportion of intervals not covering the truth amongst the reported intervals. So this is a comparison of the Bayesian FCR that I have. My target is 90%. These are the selective intervals. These are the intervals that I obtain when I do not factor in selection at all. And you can see how bad they are. These are the Lee et al. Intervals, which are frequentist intervals. They're not Bayesian in that sense. And this is splitting. Splitting again, overcomes selection bias, so you don't face the problems with splitting at all. These are the posterior means that I compute based on the different distributions, and these are the lengths of the intervals. So again, the selection adjusted posterior that we obtain by appending the truncated likelihood to the prior happens to win on a number of inferential metrics. And what I wanted to say again, connect this Bayesian business to the point estimator that I talked about, that was the selective MLE. So in some ways, the consistency, the global consistency of the selective MLE with our randomized procedures also leads to posterior consistency in the sense that we have merging of posterior inferences of two patients who may start out with different prior specifications. So that's a very desirable property to have, and it's very much connected to the fact, it just follows from the fact that the selective MLE starts concentrating around the right parameter. But I won't take more time of yours on in trying to talk about this anymore. So to wrap up, what we have right now is a very general procedure. Like James already realized that in the screening of eGenes, we were doing much beyond LASSO. We had marginal association tests, plus we had this another big beast of BH procedure. But essentially, as long as we can cast our query as this optimization problem with some convex loss and convex penalty, it's pretty easy to put this whole machinery into force. You just randomize it using this linear perturbation term, and it allows us to look beyond LASSO, which I think is a great consequence of this approximation paradigm. The second thing is, which I brushed under the carpet, I never talked about it, inference is really an arduous task in the sense that you always have to make those uncomfortable decisions about a model and a reasonable target to look at. So unlike your exploratory analysis where maybe you just have to find some interesting effects, inference comes with some difficult choices. And whatever I describe to you in some sense is very model agnostic. I can work with different models yet have the same guarantees that I was talking about and have valid confidence intervals. So nothing is tied in particular to the saturated or the full model that I presented to you throughout my talk. I went with it for consistency's sake, and that was what Lee et al. Was using, but it's not tied to that particular model. If you have a better model in mind, which is a function of selection, could be guided by selection, not guided by selection at all, I could still provide you inference with all these guarantees. What's really blocking us? Okay. So I just wanted to say the randomized inference was still, I believe, a little hard to deal with, but that's the road ahead of us. And with that, I want to wrap up. Thank you.